So I'd like to continue our walk through how these physics ideas build off each other in more of a conceptual fashion without having to appeal to explicit mathematical equations too much. So bear with me as I'm hoping that some of these ideas now seem pretty familiar. So let's go all the way back to the beginning. We start with a single point in space, okay? Then we can talk about a second point in space, and then we can talk about the distance between those 2 points in space. Then we can talk about how much distance changes over a function of time. Okay, and so when we talk about distance over time, we're talking about the concept of velocity. But then velocity can change over time. So the measure of how much velocity changes over time, that's the concept of acceleration. And so then when we moved into Newtonian dynamics, we saw the importance of acceleration, particularly in Newton's second law. Force is proportional to mass times acceleration. And so I want to continue to build now where I want to show you conceptually that momentum builds off of the concept of force. So think about force. It has that proportionality between mass and acceleration. And again, what is acceleration? Acceleration is change in velocity over change in time. It's how much your velocity is changing per unit time. So you're going to find that momentum is defined in a similar fashion. It's also proportional to mass, but in the case of momentum, it's mass times velocity. All right? So force is mass times acceleration. Momentum is mass times velocity. Just as we know that acceleration is related to velocity, I'm going to try to relate the concept of force to the concept of momentum for you. So let's think about momentum for a second. You have mass. Remember, mass is conceptually a gauge of the amount of inertia that an object has. And again, inertia is the concept that objects in motion want to remain in motion, objects at rest want to remain at rest. So an object with a lot of inertia is going to be really hard to get moving in the first place, and it's also going to be really hard to change its motion once it starts moving. And then on the flip side, something with smaller amounts of inertia is easier to move, and it's easier to change its motion. So with respect to momentum, let's say that an object of mass m has some velocity through space. So therefore, we characterize it as having a momentum of mass times velocity. Now, as we know, velocity can change. So let's say that the velocity of this object changes over time. The mass, we're going to assume, remains constant. So we essentially have, when we're talking about the change in the momentum of the object, we're talking about the mass multiplied by the change in the velocity over the change in time. What is the change in velocity over the change in time? That's the concept of acceleration. So when we talk about the time rate of change in momentum, how much momentum is changing over time, we're talking about mass multiplied by the change in velocity divided by the change in time. And so we're talking about mass times acceleration. And what's mass times acceleration? That's Newton's second law. Mass times acceleration is force. So put another way, you can rewrite force as not just mass times acceleration, but as the time rate of change of momentum. Okay? Momentum has a symbol p, and so the time rate of change of momentum would be delta p, delta t. So you can equate force with a change in momentum. So from this idea, we can talk conceptually about this concept of conservation of momentum. So imagine we have two masses, mass 1 and mass 2. And let's say that they both have velocities that are going towards each other, okay? And then let's say they collide and then bounce back. If they collide, bounce back, and there's no heat, there's no sound, there's no friction, it's just this ideal collision where they hit each other and bounce back, we call that a perfectly elastic collision. And the reason I want to use that example is because when collisions are perfectly elastic, this allows us to think about Newton's third law, okay, where for every action, there's an equal and opposite reaction. Remember, if I was to push a wall with a particular force, F, my hand is going to feel a force F pushing back in an equal and opposite fashion. So similarly, if we have two masses, M1 and M2, and they hit each other and bounce back, they are going to exert equal and opposite forces on each other. It doesn't matter if one is a semi-truck and one is a bicycle. They might have different masses, but when they hit each other and bounce back in a perfectly elastic collision, their forces by Newton's third law are equal and opposite. Now, you're going to probably imagine, like, the bicycle is going to have a very different outcome than the semi-truck. But remember, their masses are different. Just because the masses are different doesn't mean that you're going to have different forces. The experience of a force can be very different based upon how little or how much mass you have, i.e. how little or how much inertia you have. So again, two masses, mass 1, mass 2, hit each other, bounce back. So when they hit each other and bounce, equal and opposite forces. So if I'm going to define a system as my two masses that are colliding into each other, then the net force on that system is going to be zero. Because remember, they're equal and opposite forces. And so those equal and opposite forces cancel out. This mass and this mass collide, and they exert equal and opposite forces on each other. If they're equal and opposite, that means they sum to zero. If the system is just defined by these two masses that are colliding, that means the net force on the system is zero. Okay, remember, force is mass times acceleration, but we can also say that force is equal to how much the momentum changes over time. If force equals zero, that means the change in momentum over the change in time equals zero. If the change in momentum over time is zero, that means it's not changing. It's constant. And so this is why in a perfectly elastic collision, you can say that the momentum of the system before is precisely equal to the momentum of the system after. And again, this is because the net force on the system is zero, and you can relate force to change in momentum. If the net force is zero, the change in momentum is zero. When you don't have any change, it means it's constant. And so to set up these kinds of conservation momentum problems, if you know that momentum is conserved, then just account for the momentum of all the objects in your system before and account for all the momentum of the objects in your system after. And that'll help you set up the problem. So quite simply, in this problem where we have two masses of mass 1 and mass 2, they hit each other, they collide, they go back. On one side of the paper, you would say the momentum of the system before is m1 v1 plus m2 v2. And then on the other side of your paper, you would account for the momentum after, which would be m1, whatever the final velocity of m1 is, plus m2, whatever the final velocity of m2 is. So again, point in space, 2 points in space, distance between those 2 points. Change in distance over time is velocity. Change in velocity over time is acceleration. Force equals mass times acceleration. Momentum equals mass times velocity. Velocity is related to acceleration. And it turns out that when you're talking about force, which is mass times acceleration, that's also equal to mass times change in velocity over change in time, by definition of acceleration. Well, that means that force is equal to the time rate of change of momentum. You could describe force as how much the momentum changes over time. If you have a net force on a system, that means that the change in momentum over time equals zero, which means the momentum remains constant, which means the momentum is conserved.